Section 7.1 is on solving a linear system by graphing. So what we're going to do here is we're going to take a linear equation, we're going to graph it, and we're going to take another linear equation, we're going to graph it, and we're going to see, is there a point that makes both equations true at the same time? So anytime it's going to be a point that makes both equations true at the same time, we're talking about having an intersection. The point that's going to satisfy both must lie on the intersection of both of those graphs. So after we graph one line, graph the other line, see if they intersect someplace, then we're going to check and see, is that point actually the point where they intersect? And we're going to do that by checking algebraically, plugging that number back in. So here's our example. We got 3x plus y equals 11 and x minus 2y equals 6. You can graph these any way you want, but I'm going to start by graphing these using slope-intercept form. So I'm going to put them in slope-intercept form. In the red equation, my intercept is going to be 11, my slope is going to be negative 3, so there's my red equation. In my green equation, my slope is positive 1/2, my intercept is negative 3, so I start at negative 3, and I'm going to go up 1 over 2, and then I look at the graph. So you could see the red equation has an infinite number of points that make the red equation true, and there are an infinite number of ordered pairs, and they're all the ordered pairs that are on the line. And the green equation has the same thing, an infinite number of points that make the green equation true. They're all the ordered pairs that are on that line. But there's only one point that's going to make both of the equations true at the same time, and that's where they intersect. So we take a look at that point, and then we say, okay, what does that point look like? Well, to me, that point looks like it's about x equals 1, 2, 3, 4, and about y equals negative 1. So if I think that it's going to be at 4, negative 1, I can't stop right there and say, hey, that's the answer. I have to actually check it. So now checking it algebraically means plugging 4 in for x and negative 1 in for y to both of the equations. When I check it, and I plug the 4, negative 1 into the top equation, 3 times 4 is 12, plus negative 1 is 11, and so it works in the top equation. When I put it in the bottom equation, I get 4 plus 2, because negative 2 times negative 1 is positive 2, so 4 plus 2 equals 6, and it works in both of the equations. So that's our process. Graph one line, graph the other line, see where it looks like they intersect, and then check to see if that's actually the point where they intersect.